Thanks, Aaron. Hi, everybody. My name is Ken Neubauer, and I'll be here today talking about attenuation mode on the Avio 220 Max ICP-OES. We'll look at what it is, how it works, and how it can be used to solve different problems and overcome different challenges associated with ICP-OES analyses. In the past, I've given a webcast about overcoming some challenges encountered in ICP-OES. The challenges I went over were about measuring high concentrations, measuring low and high concentrations in the same sample, obtaining high precision for major elements, analyzing samples with high total dissolved solids, how to deal with volatile and organic samples, and how to take care of interferences. Today, what I want to do is focus more attention on measuring high concentrations and how we measure low and high concentration in the same sample. By going into more detail about these, I think we can understand it a little better and see how attenuation mode could help overcome these challenges. There are many examples, many different sample types and application areas where high concentrations must be measured. If we look at food analysis, for example, concentrations of minerals and nutrients must be known in order to assess the nutritional quality of the food. In addition, these must be known accurately for labeling purposes. Going hand in hand with food is the nutrient content of fertilizers. A lot of what we put in the ground is what ends up in our food, so we have to know the nutrient composition exactly of fertilizers. If we go into metallurgical analysis, the major components of alloys and steels must also be known. If these concentrations are not measured accurately, then the unique composition of the alloy or of the steels will be lost. Another example is in plating baths. When we're looking at plating solutions, the concentration of plating materials must be known, because over time you have to know when to regenerate the plating baths. So these are just a few examples, many more exist though. One of the main challenges when measuring high concentrations in ICP-OES is the linear range. In ICP-OES, the linear range is typically considered on the order of 10 to the 6th. This is definitely wider than AA, but it's also narrower than ICP-MS. When we perform measurements, we would like to be on the linear part of the calibration curve. The reason for this is for accuracy. If we look at the calibration curve on the right, which is a plot of response versus concentration, let's look at where the response is 20. We can see that has a concentration of roughly about 180. If we go up 10 response units, and we go back to the concentration, we're probably going to be about 220, 230. So roughly a change in response of 10 is a concentration change of about 40 on the linear part of the curve. However, if we go up to where on the nonlinear part of the curve, and we look at the concentration when we have response of 80, we're under 800. If we go up again 10 response units, we're going to be at about 90, and our concentration is then around 1,000. So on the nonlinear part of the curve, having the same change of response will have a huge difference in concentration. Therefore, you're always going to be more accurate if you're on the linear part of the curve, because you have smaller changes in concentration with response. Any error that may be incorporated during the measurement, during the making of the standards, is going to have less impact on the concentration when you're on the linear part of the curve. The nonlinear curve fitting, it is available. All software has this, and it can be used and it does work, but it's not ideal, again, because as we saw, a small change in the response will result in a large change in concentration. Therefore, it's best to measure on a linear calibration curve if possible. You will get more accurate results. There are a variety of options available for reducing signal intensity. One of the most common ways is to select a less sensitive wavelength. With thousands of wavelengths available, it's usually pretty easy to find a wavelength that's less sensitive than the analytical wavelength that you're currently using. We would also choose to view the plasma and radio mode, which is something very easy to do. Another common solution is to perform dilution, just dilute the sample more. We could also use alternate sample introduction components or alternate plasma and sample introduction conditions. So let's look at each of these in a little bit more detail. One of the most common ways to reduce sensitivity is to select a less sensitive wavelength. The benefits of this are that it's easy, and there are lots of wavelengths to choose from. On the Avio 550, the detector has over 6,000 wavelengths available, and on the Avio 220, any wavelength from 165 to 900 nanometers is available. So it's very easy to find an alternate wavelength. If we take a look, for example, at the wavelength table from Syngistics for magnesium, we see that the preferred wavelength is magnesium 285 and has a relative intensity of about 17,500. Now, if we need less sensitivity when we extend the dynamic range, we easily pick magnesium at 279. Again, we reduce the intensity quite a bit, about 20x, and that would work. Likewise, if we need more intensity, we can certainly go to magnesium 280 or the other 279 wavelength. However, by selecting alternate wavelengths, there are limitations. For example, there's not always other viable wavelengths. If we look at sodium, for example, at the wavelength table for sodium, the preferred wavelength is at 589 nanometers. If we want to reduce the sensitivity, we could go down to sodium at 330 nanometers. And you see this reduces the intensity quite a bit. But also look at the BEC. The BEC increases quite a bit also. So even though we're going to less intensity, we could have a more noisy baseline, which could cause problems. So there's not always viable wavelengths, other good wavelengths to use. The other thing to worry about, are there going to be new interferences present at this new wavelength? And if we're running in a regulated lab or routine methods, if we go to new wavelengths, we have to validate them and characterize them. So while selecting a new wavelength or an alternate wavelength is the easy way to go, there could also be some potential problems and challenges with it. Another way to reduce sensitivity is to view the plasma in radio mode. In radio mode, we have a shorter optical path through the plasma than in axiom mode. This results in less sensitivity, which is a good thing. In addition, we have fewer matrix effects because of the shorter optical path. And finally, in most cases, there's no need to change the wavelength. We can reduce sensitivity by just changing the view of the plasma. However, for very high concentrations, this reduction in sensitivity by looking in the radio view may not be enough, and we still may have to consider other options. Perhaps the most common way to reduce analyte intensity is by sample dilution. When you dilute the sample, less analyte enters the plasma. Another benefit is also less sample matrix entering the plasma, so matrix effects and potential interferences will also be reduced. In addition, the sensitivity can be controlled by the dilution factor. So for example, if any signal is way too intense, needs to be reduced 10 times, we just dilute the sample 10x. That makes it very easy. Unfortunately, with dilution, there are also limitations. The main one being that all analytes are affected. So say if we consider, for example, a sample which has very high level of analytes and very low level of analytes, and both need to be read in the same sample. If we dilute the sample so that the high level analytes fall on the linear part of the calibration curve, we may lose in the sensitivity and not be able to measure the low level analytes. The other consideration is we perform dilution, the sample matrix can also be changed. So if we think about it, if we have a sample, for example, made up in 5% hydrochloric acid, and if we have to dilute it, for example, 10x for whatever reason, we're going to have 0.5% acid. This means our sample now, the chemistry has changed. There's a potential for analytes falling out of solution. We can certainly perform the dilution with more 5% hydrochloric acid to remove this effect, though. And again, we're using more acid. If we change the matrix composition of the sample, we may also have to remake or change the calibration standards also to matrix match or get the matrix as close as possible. Also, as we do dilution, we have the possibility of introducing errors. We could potentially have contamination from our diluent or from our pipettes or wherever we're using to put the diluent in to perform the dilution. Perhaps one of the biggest problems, though, is potential errors. The higher the dilution factor or the more serial dilutions we do, there are more potentials for errors or mistakes. If we need to do a big dilution, we may be taking a small amount of sample and putting it into a large volume. And the smaller amount of sample we pipette, that's more tricky. It's more tricky to do, and it's easier to get it wrong. If we do serial dilutions, where we make one dilution after another, so we dilute a sample 1 to 10, and dilute that 1 to 10, well, now we have 2 dilutions, and there's 2 places to introduce error. So by dilution, it certainly works, and something that's very commonly done, but it does have its limitations that we have to be aware of. Another option for reducing analyte intensity is to use alternate sample introduction components. And some examples include less sensitive nebulizers, larger volume spray chambers, and smaller diameter injectors. So if we consider less sensitive nebulizers, a lot of these are also more robust. So it'll have the benefit of being able to handle higher levels of total dissolved solids and even some samples with particulates in it. A larger volume spray chamber will filter out the larger droplets, so only the smaller droplets will make it into the plasma. And likewise with an narrow bore injector, we're putting actually less sample in the plasma. We're actually using a lower neb flow, so we're actually bringing less sample into the plasma. The benefits for all of these is we put less sample into the plasma, we reduce intensity. But in addition, we're also going to have fewer matrix effects, so we may be able to handle more complex samples. Unfortunately, like everything else, there are limitations. If we use any of these strategies, all the analytes will be affected. So if we're trying to measure both high and low concentrations in the same sample, that's going to be difficult. In addition, for some of these changes may not be the best options for samples or matrix being measured. For example, a narrower bore injector, if we're using high dissolved solid samples, that's not good because they could clog the injector. Likewise, if we have something that needs to wash out very quickly, larger volume spray chambers wash out more slowly than smaller volume spray chambers. So it may not be the ideal solution. And this could introduce new problems. The other thing is we may have to readjust the plasma conditions. So if we use, for example, a different type of nebulizer, or we use the narrow bore injector, maybe the ideal neb flow, instead of being higher, is going to be a lot lower. It's going to be a lot different. Well, that will change the plasma. In many cases, it will make the plasma hotter, but is this going to be ideal for doing the analysis? Again, that's to be found out through experimentation. So while it has benefits of using alternate sample introduction components, we also have some limitations we have to be aware of. If we don't want to use alternate sample introduction components, another option is to use alternate plasma or sample introduction conditions. Some examples include lowering the sample uptake rate, using a different nebulizer flow, or changing the torch sampling depth. The benefits of making these changes are we can have potentially more robust conditions. In addition, we'll be putting less sample loading in the plasma, so we'll have fewer matrix effects. The limitations, though, as before, are making any of these changes will affect all the analytes. In addition, not all nebulizers work well under these alternate conditions. Some nebulizers work best at certain nebulizer flows. If you change the neb flow, make it lower, or make it too high, it's not going to be as efficient, and it may lead to sputtering, which will lead to decreased precision. In addition, some nebulizers are optimized for certain sample uptake rates. So if we use a sample uptake rate that's too low, again, we'll not generate an aerosol efficiently, which means we could have higher RSDs and worse precision. Our solution to reducing analyte intensity is using attenuation mode on the Avio 220. What this involves is reducing the light from the plasma before it enters the spectrometer. We do this by using attenuation screen, which we put into the optical path, which reduces intensity by about 90%. This only affects the user-selected wavelengths. Other wavelengths are not affected. The reason for this is that the Avio 220 is a hybrid simultaneous instrument. What this means is it will go to one analyte and acquire the wavelengths for that analyte, as well as all the wavelengths around it, so that the wavelengths that are used for setting the background points, as well as the analytical wavelengths, are acquired at the same time. So when we want to attenuate a signal, we put attenuation mode on for a specific analyte. We do the measurement, take attenuation mode off, move the attenuation screen away, and move on to the next analyte and do the analysis that way. And what we can do is we can assign to the desired analytes in the method. So if we look at an example of this method, we see that chromium, scandium, yttrium, potassium, they're all run in radio mode. But if we look down here, we do the magnesium lines and different potassium line in attenuation mode, in radio mode. And what's important to note here is our attenuation mode is available both axially and radially. And this is important because it allows different degrees of attenuation or different degrees of signal. So when we're looking at a method with attenuation mode, it's possible to run both attenuated and non-attenuated mode in the same method. In this example, we're running zirconium, boron, thallium, sulfur, and palladium in radio mode. In addition, we're also putting yttrium as an internal standard in radio mode. We are then analyzing for chromium, tin, and nickel in attenuated radio mode. Again, using yttrium as an internal standard, attenuated radio mode. What this means is we can do the analyses, acquire signal for chromium, tin, and nickel by reducing the signal. But when we analyze the other analytes, the signal is not reduced at all. And because the analysis only requires flipping a screen in and out of the way, it's very quick and adds virtually no time to the analysis. One of the benefits of attenuation mode is it gives us 4 levels of sensitivity to choose from when we're doing analysis. We can measure our signal in axial mode, radio mode, attenuation axial mode, or attenuation radio mode. So for example, let's take a look at a 1 ppm manganese signal. And let's assume that our axial intensity is 100%. If we go to radio mode, our intensity is cut by 75%. So we have 25% of the intensity. If we wanted to run in attenuation axial mode, our sensitivity is only 2% what it is in axial mode. And then if we want to cut signal further, we can run in attenuation radial mode, where our signal is only about 1% what it was compared to axial mode. So by using attenuation mode, we have the ability to dial in our sensitivity. It gives us 4 options to choose from for every analysis. So now let's take a look at an example of what attenuation mode can do. This is an example that was presented to us by a customer. They want to know how high they could calibrate magnesium. So what we did is we first looked at magnesium 285, which is our preferred line. It has decent sensitivity, and we measured it in attenuated radial mode. And what we see is we have a linear calibration up to 500 ppm. Our low standard is 10 ppm up to 500, and it looks very linear. We have a correlation coefficient of 4 nines, greater than 4 nines, so it was good. But now let's see if we want to see if we can go higher. So what we did is we used magnesium 279, which has less intensity, ran that in attenuation radial mode. And what we see here is we have a linear calibration up to 5,000 ppm. Our correlation coefficient is 0.99958, so still greater than 4 nines. We're calibrating from 10 ppm all the way up to 5,000. Now one thing we have to consider though is that even though we have a good correlation coefficient, that's not a good indication of how good the curve is over a wide linear range. Because if we look at the error associated with calibrations or with high-level standards will tend to dominate the curve. So any error associated with high-level standards, it may mean that the low-level standards aren't reading correctly. So even though we have a good correlation coefficient, that's not a good indication. So what we want to do is look at what's called the residual error, or the error of the calibration standards. And we can see this. This is definitely a better way to evaluate the goodness or the accuracy of a calibration curve. So what we do is we look at our calibration standards, a blank all the way up to 5,000 ppm. These are the concentrations which were entered into the software. These were the concentrations which were calculated once the full curve was constructed. And then the residual error is how far, or the percentage, that the calculated concentration is away from the entered concentration. So as we can see, this calibration curve, even though we went to 5,000 ppm, our lowest standard is only 3%, has a 3% error. If we look at all these, all of our standards recover within 10% of their true values, indicating very good linearity of the curve. So this really is a good demonstration that we can be linear up to 5,000 ppm. The same customer also wanted to know the linear range of potassium. So we measured a number of potassium standards at potassium 766 in attenuated radial mode. And as we can see from the calibration curve, we have a calibration coefficient greater than 4 nines again. And again, if we look at the residual error of the calibration standards, we see that everything is under 10%, indicating a good calibration curve, good linearity, and good accuracy. Now, as expected, our lower standards do have slightly larger residual errors than our higher standards. Again, this is something that's expected because the high level standards tend to dominate the curve over lower level standards. But the fact we're still within 10% shows that we are accurate even at these low levels. And this guarantees or really demonstrates linearity over a wide range. So now that we've looked at a couple simple examples, let's look at a couple applications where we use attenuation mode to overcome some problems. First application presented to us was the analysis of plating baths. In this case, it's important to monitor the concentration of the plating element so we know when it's time to regenerate the bath. The challenges associated with analyzing plating baths are that the elements are present at very high concentrations. So we want to make sure we're going to be on the linear range of the curve with as minimal dilution as necessary. The other issue is that plating baths often contain visible sludge. That means even with careful sampling, it is likely that particulates will be in the sample. So to overcome these challenges, even though dilution isn't great, we are going to do some dilution so that we try to dilute out as many particles as possible. But we do want to keep the dilutions to a minimum. In case any particles do make it into the sample, even after dilution, we want to use a nebulizer which is resistant to clogging. And finally, we're going to perform the analysis in attenuation mode to make sure we're on the linear part of the curve. So now let's take a look at the instrumental conditions we use for the analysis of chromium in a chrome plating bath. We use the Avio 220 Max, monitoring chromium 267 in attenuated radial mode. For the nebulizer, we chose a crossflow because it's very resistant to clogging, We coupled that to a Riton Scott double pass spray chamber. Used a sample uptake rate of 1 mil a minute with an aluminum injector, and we stayed with a high RF power of 1500 watts just because this could be a difficult matrix. We were able to use a plasma flow of 8 liters a minute, and we also used an auto integration range of 0.2 to 1 seconds. What this means is for a given read time we enter in the software, the instrument will evaluate the signal intensity and choose how to integrate it. So more intense signals, we use shorter integration times. Less intense signals, we use longer integration times. In addition, for our sample prep, we took all the samples and diluted them a minimum of 100x to account for particles from the plating bath sludge. So with the instrumental conditions, we performed the analysis. What we had to do is we had to confirm the results. We were given unknown samples. We weren't told the concentration. We had to confirm that the data was correct. So what we did is we compared radio mode to attenuation radio mode, and we compared different dilution factors. So if we look at the table, we see when we did our minimum 100x dilution, in radio mode our signal was saturated. But if we looked at attenuated radio mode, we see we're reading about 13.4% of our chromium concentration. So if we want to get radio mode on scale, we had to dilute the sample 1000x, and we see that comes out to about 13.7%. And attenuated radio mode at 1000x dilution, we see we're about 14%. So the percent difference from radio to attenuated radio mode is 2.6%. Gives us a pretty good indication that both answers agree. They agree with our attenuated radio mode at 100x dilution, so we know we're pretty accurate. But again, as a further confirmation, the sample was diluted 10,000x. Radio mode, again, we're about 13.2%, and attenuated radio mode, we're reading 13.6%. Again, our percent difference is less than 3%. And if we look at our percent RSD of our results from attenuation radio mode over our 3 dilutions, we see we're 2.4% for our RSD. So this tells us we have accurate results. We have good agreement between different dilutions and good agreements with radio mode. The benefit of using the attenuation mode is less dilution is required. We can do the analysis at 100x dilution, which means there's less chance of error and less chance of contamination. And the fact that we had attenuation radio mode allowed us to make more of these comparisons and really confirm the results. Another application we looked at was the analysis of wine. And the first question to ask is, why do we choose the Avio 220 Max for this analysis? And there are a few reasons. First, that there are a limited number of elements, generally less than 12, although the number of elements varies based on local regulations. We have customers who are doing wine analysis by Flame AA, some using ICP-OES, some doing ICP mass spec. It really depends on what the local regulations are, what the wineries want to do. But perhaps the greatest reason is there's a wide concentration range. If we look at arsenic, cadmium, and lead, these are toxic elements, so they should be present at low levels, hopefully. Another common analyte is silver. This is added to the wine as a deodorizing agent, as typically present at low levels. 3 other elements that are important are copper, iron, and zinc. These are oxidation catalysts that indicate the quality of the wine, and they're usually present at moderate levels. And finally, we have the minerals, calcium, potassium, magnesium, and sodium. These usually indicate the stability of the wine and are present at high concentrations. Another reason for choosing the Avio 220 Max for this work is that it has very high sensitivity due to its unique optical properties and optical design. What this allows us to do is use radioplasma view for everything. This will reduce the carbon background and matrix effects. In addition, because of the high sensitivity, we'll be able to see the low-level elements, silver, arsenic, cadmium, and lead in this case, all that are hopefully present at low concentrations. In addition, because of the high sensitivity, we can use a lower sample uptake rate and a narrower bore injector. Both of these will lead to less plasma loading, which will increase the signal background, which will allow us to measure these low concentration analytes better. In addition, we also have attenuation mode, which we could apply for the high-level elements, calcium, potassium, magnesium, and sodium. This will allow us to get linear calibration curves up to high concentrations. When performing wine analysis, there are several challenges that have to be overcome. The main challenge is presented to us by the organic components. First, wines are generally 10 to 18% ethanol. Since ethanol is a boiling point of 78%, that makes wine a volatile organic compound. So this could cause problems with plasma stability. In addition, there are other organic components in the wine samples from the grapes. And so some of the problems we have to overcome are keeping the plasma lit, We're going to have a high carbon background from all the ethanol and all the other organic components. We have to worry about keeping the signal very stable, again, because of volatile samples. They could cause plasma instability. We're going to have a wide analytical range. We're talking low ppb, less than 10 ppb for silver, arsenic, cadmium, and lead, up to high ppms, over 100 ppm for calcium, potassium, magnesium, and sodium. As a matter of fact, potassium is generally present in wines at around 1,000 ppm, so we have to measure that accurately. So how do we overcome the challenge of wide analytical range? Again, we use the high sensitivity of the Avio 220. This will allow us to measure low concentrations, low concentration elements. It will allow us to use a low sample uptake rate, using 0.5 mils a minute. And will allow us to use radioplasma view, so we'll minimize the carbon background as well as some matrix effects. We use attenuation mode to reduce the sensitivity for the high concentration elements, and the low concentration elements are not going to be affected, so those are analyzed in non-attenuation mode. These are unique characteristics of the Avio 220. So how do we deal with the volatile and organic compounds? Well, solutions, we use a low sample uptake rate, 0.5 mils a minute. We use a narrow bore injector, combining with the low sample uptake rate and a low nebulizer flow of 0.5 mils a minute, we're limiting the plasma loading, which has the other benefit of reducing matrix effects and the carbon background. We're also going to use a high RF power, high plasma power of 1,500 watts. We're going to increase the plasma flow to 12 liters a minute because we're still going to be getting volatile organic compounds in there, so a little bit higher plasma flow will allow for more stable plasma. And we'll perform our analyses in radioplasma view. And because the Avio 220 has high sensitivity, it allows these conditions to be used for this analysis. The benefits to doing all this is we're getting less sample into the plasma, which will increase stability. We'll have less matrix suppression, which will allow us to measure lower concentrations. We're going to have a lower carbon background, so we'll have fewer interferences, and we're going to have a higher signal background ratio. Okay, so let's talk about the samples and the sample preparation. We looked at 4 different wines, Pinot Grigio, a Chardonnay, a Rosé, and a Pinot Noir, and they had alcohol content of about 12%, with the Chardonnay being up around 13.5%. We got this right off the bottles. So what we did is we filtered the wines through 0.45 micron filters because all the wines had visible particulate matter in them. And we noticed is that the darker wines generally had more particulate matter. So we actually filtered them a second time through 0.22 micron filters to try to capture to remove as many of the particles as possible. We then acidified the wines with 1% nitric and 2% hydrochloric acid. And this took a little while to figure out. We used the nitric acid to stabilize most of the elements, but we noticed that our silver spike recoveries were always low. But we found if we added the HCl, 2% HCl, the silver was stabilized. And especially in the darker wines, we saw that the silver was not stable, and this is presumably due to the high sodium chloride content of the darker wines. We didn't investigate in detail why, we just found the solution to the problem. So let's take a look at the calibration. We've made our calibration standards in 1% nitric, plus 2% hydrochloric acid, and 12% ethanol. Most of the analytes we analyzed in regular mode, and we can see our cadmium was our lowest expected concentrations, so we calibrated from 2.002 part per million up to 0.01 part per million. And then for our analytes, for our minerals, we analyzed those in attenuation radio mode, with potassium being the highest. We calibrate that up to 1,000 ppm. And as we can see, if we look at the spectra on the right, these show spectra of our calibration standards across the range. So for cadmium, we clearly see a peak down 0.002 ppm, which is clearly separated from the background, so it's easy to see. And likewise, if we go up to potassium at 1,000 ppm, we see that we can easily see the peak there. And these all gave linear calibration curves. So if we look at the results, these are the results from the wine analysis. The x-axis shows our analytes. The y-axis shows our concentration in milligrams per liter. Each bar represents a different wine. Pinot Grigio is light yellow, Chardonnay is slightly darker yellow, Rosé is medium red, and Pinot Noir is dark red. And these kind of correspond to how light and dark these wines were. So if we look across, we see there's definitely a wide range of analyte concentrations. We're measuring cadmium concentrations down below 0.001 ppm, or below 1 part per billion. We're seeing that potassium we're measuring up around 1,000 ppm. And if we look, we notice that all the analytes in all the wines are fairly constant in concentration. The exceptions being arsenic, which is definitely higher than the Pinot Grigio and Chardonnay. And actually, arsenic was not detected in the rosé at all. We also see some variation in copper, where the Pinot Noir had more copper than the other analytes. So that's great. We saw that, and we also see that silver was not detected in any of the wines. So that's a good first step. Those are results. They're repeatable, but we want to try to prove accuracy. So what we had to do is spike recoveries. So what we did is we did spikes at the Italian regulations. We're working with one of our customers in Italy on this. So the Italian regulations are shown here, and our spike levels are shown here at the Italian regulations for the different analytes. So we had spikes from as low as 0.1 ppm for cadmium, silver, and lead, up to 1,000 ppm for potassium. And if we look at our y-axis this time, is our percent recovery, and we see that our recoveries for all our spikes and all our wines were between 90 and 110%. So this just shows all our recoveries are within 10%. So it shows we're getting accurate results at the high concentrations. And again, these are at the Italian regulations. Well, we want to see how accurate we were at lower levels. How much confidence do we have when we're looking at lower concentrations? So we spiked everything at lower concentrations. In this case, our low spike was cadmium at 0.003 ppm, and our high spike was 50 ppm of sodium. We chose not to spike potassium or the other analytes or the other, minerals, because they're just present at high concentrations. Spike recoveries, trying to go too low, you're not going to see anything. But again, we see that all our spike recoveries were within 10%, which indicates accuracy. So we've seen both accuracy at low concentrations and high concentrations. So I'd like to thank you for attending this webinar. Just to give a quick summary about attenuation mode, it shows that we have a selective attenuation of the analytical signal. What this does is it overcomes limitations of other strategies that are commonly used for reducing analyte signal. We can attenuate in either radial view or axial plasma view, and this actually gives us 4 different sensitivity options when we're doing an analysis. The main benefit of attenuation mode is it extends linear range. It's also then it's the perfect solution when we're trying to measure both low and very high concentrations in the same sample. We want to measure them accurately and consistently, and attenuation mode allows that. I'd like to thank you for your time. I'd be happy to try to answer any questions now. Thank you.
All right. Well, thank you very much, Ken. That was a good presentation. Hopefully everyone got some good information out of it. So I will now move on to the question and answer period. I'm just pulling up the questions here, see what people submitted. All right, Ken, you there? Still there with me?
Yes, I am.
All right, fantastic. All right, so we have a couple questions. The first one, viewer is asking, in attenuation mode, why are other wavelengths not affected?
Okay, this has to do with the optical system, the way it's designed in the Avio 220. What we do is we look at one analyte at a time. So we simultaneously acquire the data for the analyte of interest and all the wavelengths around there, so the background points can be set. Therefore, when we do attenuation mode, we put the screen in, the attenuation mode in, just for that analyte. Then when we run analytes in non-attenuation mode, we remove the screen and we look at the other analytes then. So that way we're only affecting the analyte that we want to and not any others.
Yeah, it's perfect. It kind of ties into the next question is, can I run an analyte in both attenuated and non-attenuated modes in the same method? And
yeah,
basically,
absolutely.
Yeah, right?
Yep, that's why you do that all the time during method development. If I have a high level, if I want to see which is which mode will be better for me, which will give me better answers, I'll run them both at the same time or in the same method. So I'm only running the
And
sample
sometimes,
once, it'll measure both, and I'll have both answers for
yeah.
me.
And sometimes when you have a whole bunch of unknowns, right? And you know that
Exactly.
some of your unknowns could be really high in that particular element. Sometimes I'll run in both. So I'll have, it actually effectively, extends your working range, right?
Exactly. Yep. Great
Yeah.
point.
And sometimes I'll name them different, like sodium low, sodium
Exactly.
high, or whatever, Yeah.
Exactly.
Next question, is there a time requirement to switch from a normal to attenuated modes?
It takes about 1 second to switch. So what'll happen is if there are several analytes in attenuation mode, it will run all those together. So it'll take about a second to switch the attenuation mode. It'll run everything in attenuation mode, second to switch out and run everything in normal mode. Or like I mentioned, you can run attenuation, axial attenuation, radial. If you do that again, 1 second to switch the attenuation mode in and out for each mode.
Yeah, but
So
it's
that's
pretty
as minimum
fast.
amount of time.
It's not that much overall.
No.
Really. And if you need that extension of your working range, it really works well. Okay. Oh, question here on the nebulizer. What nebulizer did you use for the wine analysis?
For that, I was using our standard Meinhard nebulizer. Other nebulizers could be used, but I was using the Meinhard. There are nebulizers that are optimized for lower sample uptake rates. So if you need a little more sensitivity, you can use one of those nebulizers. And some of those nebulizers are also optimized to have be more resistant to clogging. So you can certainly use that. Generally, when I'm doing my application work, I try to use the components as standard as possible and only switch when I see a need to.
Yeah, so I guess the kind of continuation on to that after that question was a statement. And then essentially, we've tried to look for low levels of cadmium and lead in baby food. And we keep seeing that the calculated concentration comes back as negative in the report. Well, I mean, for me, just negative in the report can be a couple things. Can be the calibration bias. Could be your blank. Could be higher concentration than your actual samples.
You should also look at your spectra when you see negative. If for
Mm-hmm.
some reason there's a matrix effect, you may have either the baseline's dipping by your analyte, or if you have an interference or another unexpected peak. If that goes higher, it could be hitting on one of your background points, causing the background point to be higher than normal. So you'd be subtracting a negative value.
That's what I always do in ICP-OES is
Exactly.
always I love the examine window in the software, so I go into the examine window and I look at the spectra. That's the beauty of ICP-OES. So you get your spectra and all the wavelengths around it, and you can look at how it's integrating the spectra and how you're correcting for background shift. And as Ken said, if there's interference, you can usually see it in the spectra. So that a lot of the time the calculated values being negative, you're right, an OES is an interference or background issue or something like that.
And that's something I've known if I'm doing work and I know things are supposed to be working and all of a sudden I see a strange value like that. First I do is look at the examine window and check out the spectra. And 9 times out of 10, it's a peak that showed up where I didn't expect it to, which is affecting my background points or the baseline is drawing.
Yeah. But yeah, if you're looking for more sensitivity, concentric nebs typically will get a little bit better sensitivity. So it also somewhat depends on your setup and flow rates and so forth.
And there are a variety of nebulizers out there to choose from. There are many different types, all have their benefits. Like I said, I just use my standard setup when I'm for as much as I can, and change when there's a requirement to change.
Yeah, sometimes we go to less efficient nebulizers too, just to reduce the amount of stuff get into the plasma. But yeah, and as always, you can feel free to reach out to me if you have any other questions or specifics on the data. Sometimes sending over a data set to your local application scientists or even myself I don't know where you are in the world, but yeah, you could always reach out and send the data set through the data manager, and you just click archive data set and send that zip file off to someone in PerkinElmer. We can help you review it. All right. I think that's actually it. We went through not too many. There was a question on, do we get the copy of this presentation? And yeah, we always send out a link to the recording of these webinars. Usually I send a link. It goes out about 24 hours after the end of this webinar. So, so you should see an email with a link to the recording, so you can refer to it anytime in the future. And in the meantime, so I want everyone to, have yourselves a great time. Thank you for attending, and to check out the other webinars, please go to perkinelmer.com/atomic spectroscopy webinars, and you'll get that email too as well. Again, thanks, Ken. Thank you for presenting today. That was great. And thank everybody for attending. And feel free to reach out if you have any questions or have any other topics of interest that you'd like to hear from or see. All right. Thank you very much. Have a great day.